Hello, in this video I would like to show you how you can perform a beam member check according to the ASME BTH-1 standard that has recently been added to the SDC Verifier library in the 2024 R2 release. For this purpose I will refer to this simple spreader beam example for which the FEA model is already created in SDC Verifier, but I will also refer to some manual inputs and hand calculations gathered in this document that will be also available to you on our website. As we can see, we will be designing this simple spreader beam composed of just one beam section. We will want it to fulfill the requirements of the ASME BTH-1 code, the 2023 version. We've chosen to design it for a rated load of 25 tons. And we've also chosen design category B for this lifter, which results in a nominal design factor of 3. We will not be focusing on fatigue design, so the rest of this information is not relevant for us. Here we can also see a brief description of the geometry and material. So we will want to check whether an IPE 600 section composed of a S275 steel can fulfill these requirements, and the chosen length of the beam is 4.5 meters. Here we can also see some other properties of the cross section. All of these inputs are already included in our FEA model, which can be checked in the model section in the tree. As we can see, the material, the property, and the according FEM loads and constraints. But let's move in the direction of the standard itself. The one step we need to perform before we can get there is to recognize the structural members in the model. In this case, we have a model composed of just beam members. This can be simply checked by turning off the thickness, which we can see it's just a 1D element. So for that reason, we can use the beam member finder either from the recognition section in the tree or from the recognition section in the top ribbon. Here we can open the beam member finder tool, and all we have to do is to click the find button. In my case, the beam members are already recognized, so we can just confirm. Now moving on to the standard. To add the standard, you can either right-click standards in the tree and go to add, or you can also use the top ribbon in the standard section. Here you can go to the ASME and choose the relevant version for your project. In our case, it's going to be the 2023 version. As always, we try to include descriptions for all of our standards. So here you can check which document it refers to, which sections are included, and also which shapes are supported. The other part of the window is the manual input from the user that couldn't be read from the FEA model. So let's just quickly go over all of the inputs we have to do. Let's start with the section build type. You can always hover over these names to see some additional info. In this case, we need to choose whether a section is rolled or built up. To do that, we open the characteristic window. And in this case, we can simply use the rolled section to all our properties. In this case, just the IP 600. Moving on to the next one, we have the section net area. So let's open the characteristic window. We can also always refer to the description. In this case, we see that it's the effective net tensile area. So we can know that it's going to be used in the tensile check. In this case, we focus on bending, so we can simply use the default value of 0. The next characteristic is the beam brace type. Let's again open the characteristic window. And again, we can refer to the description. We can see that this value is required to calculate the value of the CLTB coefficient, which is the torsional buckling strength coefficient. So we can also leave the default value, in this case yes, which means that the beam is braced against twist or lateral displacement. And the remaining two characteristics that we need to input is the CMX and CMY. If we would go to the description, we would find out that they are used for the interaction equation between bending and axial stresses. So in our simple case, we can also leave them as default. But in case at any point you would need some additional info, as you can see, all of these inputs have the correct references to the sections of the standard. So we can always check which value you would have to input for your specific case. The next option is the calculate CB coefficient. As we can see, we can either leave it on using the moment diagram from paragraph 3.2.3, or we can use a user-defined value. In this case, I will leave it as it is. Additionally, we also get the info whether we have any materials with undefined yield in our model. In this case, it displays 0, so everything is fine. And in this standard, in this implementation, you also have two additional options. You can either calculate asymmetric shapes as symmetric, in case you have any in your model, or you can use the calculate beyond limits option, which lets you obtain results even for members that don't fulfill the requirements from the table or the paragraph that are referenced here, which are usually slenderness requirements or width to thickness requirements. This may be useful in cases where your slenderness is just slightly above the limit. And the last input that we need is the nominal design factor. You can also hover it to get some additional info, but we already know from our document that for a lifter category B, we need to input the value of 3. And the last thing is the selection. In this case, an I-beam is in fact a supported shape, so everything should be fine. So we can confirm everything with OK. As we can see, the standard has been added to the tree, and it includes 16 checks. Some of them are property checks for some geometrical properties, and the rest are general checks related to loads as well. So let's just quickly go back to our document and see how the procedure would look like in manual calculations. As we can see, we would have to check the flange slenderness according to the limit from the table. We would find out that the flange is compact. We would have to check the lateral bracing interval to find out which allowable bending stress we can use, which allowable bending stress equation specifically. And then we just calculate the bending moment and stress. For a simple beam, it uses the pretty simple equation of multiplying the load times the length over 4. And at the end, we can compare these values, or we can divide them, which is what we usually do in SDC Verifier, to obtain the utilization factor. So this result gives you the information that 93% of the allowable bending stress has been utilized when lifting a 25-ton load. So to do it faster in SDC Verifier, we know that we want to perform a bending check. So we go to the bending check in the tree, and we can either add a table or a plot. In this case, the table will be more convenient. We can add the table. Next, we need to choose the individual load, in this case, or the load itself. But in this case, we have just one individual load because it's a very simple example, and we can use the extreme table type. We can also use the expand, but in this case, we're looking for the maximum value. And all we have to do is to fill the table. It usually takes just a second, and as you can see, we obtained the results. The values are exactly the same as in the document that we just referenced, so we can see the utilization factor for major axis bending is 0.93, the allowable bending stress is 100.83, and the calculated bending stress from the FEA results is 93.71 megapascals, which, as we can see, is the same value in all cases. This document also goes into more detail on setting up the FEA model and performing the intermediate calculations, so you can check it on our website for your convenience. And just to be sure, and at the end, as you can see, it compares the values, which proves that we obtained exactly the same results with both hand calculations and using SDC Verifier. I hope this clears up a general use case of the beam member check of ASME. More checks are planned for the development, specifically the weld checks, the bolt checks, and probably also the fatigue check. So keep an eye out for that in the future. But for now, thank you for your attention and see you next time.